Good morning, good afternoon, good evening, wherever you are in the world. My name is Rongbo. I'm currently a visiting professor at Keio University in Japan. At the time of writing this paper, I was a postdoc researcher at Technical University of Munich in Germany. And today, the topic of my presentation is construction automation and robotics for concrete construction. Case studies on research, development, and innovations. So first, why construction robots? So construction robots can increase productivity. The construction sector lags in productivity growth, as we all know. Global productivity growth in the construction sector has averaged only 1% per year over the past 2 decades, compared to 2.8% for the total world economy and 3.6% in manufacturing sector. Using construction robots to increase the productivity becomes critical to the development of the construction industry. And also, construction robots can reduce waste. The notion of robot-oriented design, which I'm going to touch on in detail in just a moment, advocates for the industrialized modularization and prefabrication of building parts, components, modules, and units, enabling rapid on-site assembly and disassembly, which can contribute to waste reduction in the construction sector. And furthermore, construction robot can improve labor safety. For example, there were more than 3,500 fatal incidents at work in EU 28 member states during 2020 a year, of which about 1/4 happened in the construction sector. The reduction in the chance of working at heights as well as exposure to toxic material by applying construction robots can reduce the chance of fatal accidents and other injuries on the construction site, obviously. And last but not least, construction robots can mitigate labor shortages. Many countries and regions have already experienced labor shortages in the construction sector, especially for high-skilled ones. A good example is the city of Hong Kong. The advantages of this automation and robotics can mitigate these shortages. So first of all, I'm going to just introduce a little bit about the brief history of construction robotics. So the first stationary construction robotics debuted in the late 1960s in the Japanese modular prefabrication streamline of the legendary Sekisui Han M1, which was actually part of the doctor thesis of Dr. Ono. And later on, there are single task construction robots, the STCR. From the late 70s, the first on-site construction robots were developed by Japanese general contractor Shimizu. Due to the lack of skilled labor, low construction quality, and bad public image, and so on. And since then, about 50 construction robot systems have been developed by major Japanese contractors in the 1980s. Here are just 2 examples, as you can see here. This is a fireproof spraying robot, and this is a concrete leveling and finishing robot developed by Shimizu Corporation in the 70s. And as a result of this all this development from the 1990s, on-site automation construction sites also were developed. For example, this is the so-called smart system. As you can see here and here, from the exterior view to the interior view. And this type of system are also called sky factories, which was an integrated system to build oftentimes high-rise building using construction robots, and so on. And here are just another 2 examples of this automated construction site. For example, the big canopy developed by Obayashi and the Amara system developed by Kajima. And on the opposite, there will also be automated deconstruction sites. For example, this is the Haida method developed by Takinaka and the Tekrab system developed by Tesla Corporation. And further innovation push was triggered by earthquakes, landslides, volcano eruptions, and tsunamis, and all other kinds of natural disasters since the 2000s. After this, tele-cooperated construction robots were developed, and since 2010, autonomous construction machinery such as scrapers, graders, rollers, bulldozers, trucks, and excavators for large infrastructure and large engineering projects were also developed for dams, roads, bridges, tunnels, and so on. So this is the SMAST system, solid material assembly system. where the earthquake-proof reinforced concrete block assembly and disassembly robot was developed and tested in Japan between 1984 and 1988. In this project, Professor Thomas Bock, the co-author of this paper, developed this milestone notion of robot-oriented design, which suggested that architects and engineers should already consider the application of robotic technology on the construction site when designing the compliant building parts and components, eventually achieving shorter on-site assembly time and higher profitability. As you can see here, the concrete block was specially designed for the robot to grab, which can simplify the design of the robot. And here's just another example of this robot-oriented design, where on this facade, the facade cleaning robot and painting robot, it can travel upside down through the rails, which was already integrated in the building facade. And I further categorized all the different type of construction robots into 22, 23 different categories, from low integration level to high integration level. And here is the so-called X8 house, which was one of the first real applications in Europe for construction robots. It offers a 100 square meters of living space on 2 stories, with a bathroom, toilet, building service module without a basement, which can be prefabricated in 8 days by specially designed portal robots, as you can see here, and also assembled in just 8 hours, and which was also sold in 80,000 German marks at the time, so which was very affordable. Here's just another example that we developed for Hong Kong. So this is a facade processing multifunctional robot. And also during this project, a semi-functional prototype also was developed, which includes also functions such as painting, cleaning, grinding, inspection, marking, installation, and so on. Was also designed, built, and tested in a laboratory environment as a proof of concept. The robot can work on the facade of high-rise public housing buildings in Hong Kong and beyond, in collaboration with the workers. And here you can see some further images for the simulation of this robot working on site, and also the semi-functional prototype, which was displayed in the Hong Kong Innovation Center. And here is just another example of this construction robot endeavors we did over the past few years. This is the Hepasto system, which comprises of facade module installation, cable-driven parallel robot, CDPR, with 8 cables, and also a MEE, a modular end effector, as you can see here. And this robot can potentially achieve 220% productivity gain compared to conventional facade installation method for a typical job, let's say, for example. And the robot is theoretically worth investing in Germany, as well as the majority of the G20 countries, according to a cost-benefit analysis study during this project as well. And here's just another example of this wall painting robot developed by this our startup, ARE23, managed mainly by Dr. Wen Pan, colleague of mine, and the co-author of this paper as well. So in this system, a 3-axis robot for interior surface encoding or painting that can autonomously scan the surface, determine the optimal path, and screen hard-to-reach surfaces were developed. The initial test result suggested that both variants of this robot, the Titan range and the compact range, can potentially boost the productivity by 250% compared to conventional manual wall spraying method. And here's just some other spin-offs and startups yielded from this our team over the past few years. So to summarize, construction robots do not mean simply applying industrial robots on the construction sites, but to design professional service robots with special kinematics that can be adapted to the condition of construction tasks and sites. Construction robotics can potentially play a significant role in concrete construction and beyond by improving productivity, reducing waste, enhancing safety, as well as mitigating labor shortages. And it is also a highly interdisciplinary research and development field that requires close cooperation of various expertise and fields, including but not limited to architecture, civil engineering, robotics, mechatronics, informatics, and construction management. So the research and innovation endeavors represented by the projects and the entrepreneur activities conducted by the chair of building realization and robotics at TU, along with our in-house spin-offs and startups such as CREDO, ARE23, KEWAZO, and ExlenTec Robotics, over the past few years have contributed significantly to the knowledge and know-how in concrete construction and beyond, which also shows that construction robotics is becoming a crucial part of the construction sector today. And thank you very much for your attention. I'm ready for some questions. Thank you.